Okay, we're now going to look at example B. We want to sketch the curve y equals x to the power of 4 minus 9. Now, again, this is not a transformation of a basic curve. If we knew what the basic curve y equals x to the power of 4 looked like, then we could just slide it down 9 units and draw it. But we don't know the basic curve for x to the power of 4. So that's why we have to go through this different process where you have to get where it cuts the x-axis, the y-axis, get turning points, and get their nature. So let's start off with where it cuts the x-axis. So any graph cuts the x-axis when the y-coordinate is 0. So we set y equal to 0. So replace y with 0, we're going to get 0 equals x to the power of 4 minus 9. We're then going to move, because there's only one x term, move the number term to the other side. And then we're going to take the fourth root of 9. You know, if this was x squared, we would take the square root, so it's x to the power of 4. We're taking the fourth root now. Be careful. When you take an even root of a number, there will always be a positive and a negative answer. Okay, because remember, if you took the square root, it would be plus or minus the square root. So it's the same if it's the fourth root or the sixth root or the eighth root. Any even root will give you two solutions. An odd root will just give you one solution. So we've got x equals plus or minus the fourth root of 9. Now, it's okay to leave your answer like that. Yes, you could type it into the calculator, but the weird thing is the calculator gives it as a decimal. And the reason I'm saying that's weird is because if you actually look at the fourth root of 9, what you could do, and you don't have to do this, but what you could do is write 9 as 3 squared, and then you're taking the fourth root of that. Now, the fourth root also means the outer power is a quarter. You know, if you see something with a power of a quarter, you know that means the fourth root. So that's the same as 3 to the power of 2 all to the power of a quarter. And then, because there's an inner and an outer power, you could multiply those and you would get 3 to the power of a half, which is obviously just going to be the square root of 3. Now, the amazing thing is, right, the fourth root of 9 is actually the square root of 3, but you would think if you type that into your calculator, it would give you the square root of 3. It actually doesn't. The calculator brings up 1.703, something like that approximately. But the root 3 is about 1.703. So that's the weird thing. So it actually gives you root 3. So the two solutions here are x equals plus root 3 or x equals negative root 3. But as I say, don't get too bogged down and say, oh, I wouldn't know to do that. If I left it as plus the fourth root of 9 and negative the fourth root of 9, that's fine because they do give you the same value. But I'm just showing you that. It's actually quite interesting the way the calculator can't actually compute that. Anyway, we've got where the graph cuts the x-axis. What about the y-axis? So cuts y-axis, we're going to set x equal to 0. Okay, so we'll go to our curve, replace x with 0, so we're going to get y equals 0 to the power of 4, subtract 9, so that's just going to give us negative 9. So far so good. Okay, next thing, turning points. So remember, the x-coordinate of any turning point occurs when the general gradient is equal to the actual gradient, which is 0. So in other words, we set dy by dx equal to 0. Now, that means we have to differentiate the curve, first of all, to get the general gradient. So the general gradient, dy by dx, is equal to 4x cubed And then differentiate a number, remember you just get 0, so it's 4x cubed. Okay, so we're now going to get the x coordinate of the turning point. So x coordinate of turning point. We are going to set dy by dx equal to 0. And then we're going to solve it. So we set 4x cubed equal to 0. Divide through by 4. So we're going to get x cubed equals 0. Take the cube root of the other side. Well, if you take the cube root of 0, you just get 0. So, in other words, 0 times 0 times 0 gives you 0. So x is just equal to 0. So there only appears to be one turning point, and the x coordinate is 0. So now we're going to get the y coordinate of the turning point. So what we do is sub the x coordinate of the turning point back into the curve. So we replace everywhere we see x with 0. So we're going to get y equals 0 to the power of 4 minus 9. So y equals 0 to the power of 4 minus 9. So that's just going to give us negative 9. So we've now got the coordinates of the turning point. So the turning point is 0 minus 9. Now we're going to get its nature. Is it a max or a min or a point of inflection? So we're now going to get the second derivative. So nature of turning points. So we need d2y by dx squared. So to get the second derivative, you go back to the first derivative here, the general gradient, and you differentiate again. So we're going to get 12x squared. So d2y by dx squared is going to be 12x squared. Fine. We're now going to sub the x coordinate off the turning point into the second derivative to work out what type of turning point it is. So the turning point, remember, had an x coordinate of 0. So when x equals 0, we chuck it in. So the second derivative, d2y by dx squared, is equal to 12 times nothing squared, which is equal to 0. Now we're in trouble, because if the second derivative is 0, well, it doesn't conclusively tell us. So it could be a max, it could be a min, or a point of inflection. So at the minute, we're no wiser. So could be a max, or a min, or a point of inflection. So what's the strategy then? We now have to investigate the sign of the actual gradient around the turning point. So now we need to investigate the sign of the actual gradient around the turning point. So what that means is we're going to rule a table. So we're going to rule a table. 2 rows. The top row are the x values. Now, the middle x value is going to be the x coordinate of the turning point, which is, if we go back down here, 0. So x coordinate of the turning point goes in the middle. You then choose 2 x values either side of it. So we're going to choose an x value before it and an x value immediately after it. So I'm going to pick -1, that's immediately before 0. I'm going to pick +1, that's immediately after. Try to keep the whole numbers as well. You don't have, you could pick minus 2 and 2, it's fine, as long as they're either side of it. One here obviously negative to the left, one positive to the right. And what we're going to do is we're going to sub all of these x values into the general gradient, dy by dx, to get what the actual gradient is. So the second row is going to be the general gradient, dy by dx, and I'm going to write out its formula again. So dy by dx was 4x cubed. So we're going to chuck each x value into dy by dx to get the actual gradient. So let's chuck in minus 1. So you cube minus 1, it's still going to be negative. Remember, if you raise a negative to an odd power, it's still going to be negative. So that's still negative 1. Multiplied by 4 is negative 4. So in other words, the sign of the actual gradient when x is minus 1 is still negative. We're not worried about its value, we're just worried about its sign. It's negative. So what that means is the actual gradient of the tangent to the curve where x is minus 1 is sloping down. Negative gradient. Tangent is sloping down at that point. We're then going to chuck the x coordinate of the turning point in. Now, at the turning point, the sign of the actual gradient is always going to be 0. In other words, a horizontal line. So let's prove it. Chuck in 0 here. 0 cubed is 0 times 4 is 0. So the actual gradient is 0, and 0, remember, is just represented by a horizontal line. Okay, if the actual gradient is 0, then that means the tangent at that point is a horizontal line, because that's where the turning point is when x is 0. So tangent to the left of the turning point is sloping down, then at the turning point it's horizontal. What's happening when we chuck in 1? Well, when we chuck 1 in to the general gradient, we're going to get 1 cubed, which is 1 times 4 is 4. So the sign of the actual gradient is positive. So that means the tangent is sloping up immediately after the turning point. So what type of turning point is it? Well, it's got to be a minimum. Okay, it's got to be like a U-shape minimum. Tangent sloping down, then horizontal, and then sloping up. So therefore, it's a minimum turning point. So 0 minus 9 is a minimum. If you drew your table and you had the first tangent sloping up, then the middle one horizontal, and the next one sloping down, then that would be a maximum. But in this case, it's a minimum. So we've now got all the information together. We know where the graph cuts the x-axis, we know where it cuts the y-axis, we know where its turning point is, and we know what type of turning point it is. So now it's time to sketch. So again, ruler axes, y-axis, x-axis, origin. Go back to the start. It cuts the x-axis at positive root 3 and negative root 3. So positive root 3, somewhere there. Negative root 3, the same distance to the other side. Okay, the turning point is at 0 minus 9. So 0 minus 9 is going to be roughly, again, just a sketch down there. So that's our turning point, 0 minus 9. And we've worked out that the turning point is a minimum. So at the turning point, it's going to be a lovely kind of U shape like that. So all we're doing now is completing the shape. So it's clearly going to go up this side, cut it minus root 3. It's going to go up on this side and cut it root 3, positive root 3. So it's going to look like that. And then over here, it's going to look like that. And again, label it. So that is the curve y equals x to the power of 4 minus 9. Now, the curve is symmetrical about the y-axis. You will find that a lot of curves where you have a single x term and the power of x is an even power, you will find that they'll all be symmetrical about the y-axis. They cease to be symmetrical when there's maybe more than one x term, or you've got odd powers of x as well. That's when they cease to be symmetrical. So it's very, very like your x squared curve. That's because, again, the power is even.